Can you hear me? Okay. So we have now this session is about CST particle simulation. I have to click on that. Yes. Yes. And here is the outline, our presentation now. We have modeling and Helix TWT. We have CAD model import here, and we define simulation parameters, and we obtain and discuss simulation results, and we have conclusion here. So this is hot test analysis, which means that we have electron beam here, and we have a TWT helix flow wave structure here. We define particle sources. We don't have electron gun, but we define particle sources here, and we have a helix flow wave structure, and we have our input and output couplers. And how to we design this? We have this flow chart here. Choose an application array using any project template and CAD model import, or you can design your own. And you can update your material properties. You should define 4 ports, input and output ports. You set the frequency range and check the background and boundary conditions. And you define particle source and emission properties. And you define field and particle monitors. You define focusing field, and you define the excitation signal and input power, and you check the mesh, and you run the simulation. So this is hot test analysis for CST particle studio. So we have CAD model, which is in the CST example. This is CST example. You can access from CST program. So this is our TWT. This is helix flow wave structure here, and we have here RF output, and we have RF input, and we have dielectric support rods here, 3 dielectric support rods. You can see this one actually, and we have here a cylinder to stimulate or to define electron gun parameters here. This electron gun parameters input. We define particle sources from
particle in cell.
Yeah, this is particle in cell simulation. So we define particle sources by using this surface. So this is our CST. This is our CST window. So we choose our problem type here by using this particle, and then we use particle in cell here. We select this part in order to have particle simulation. Before that, we have that model, and then we choose this particle in cell. And we can define a particle circular source. We use this simulation button here, and we use particle
polarization, circular polarization.
I mean, this is just a circular source. This is electron beam, to define electron beam.
This is electron.
Yes. So this is, we use particle sources here, and we use particle circular source. We choose particle circular source. And before that, firstly, before that, we should select this surface by using peak. You select modeling button, and then you can use peaks, or simulation button. You can use peaks here, and then you can select this surface. After that, you can select particle sources. After simulation button, you can use particle sources and define particle circular source. And if you select this, you have this window, DC emission settings. This is general button. So we can write here current interval. So, and this is rise time. We can define this, and then we can, yes, actually, this is the first window. We can say this is the first window of particle circular source. This is the first window, and if you choose P particle in cell emission model here, we can choose DC, and then if you select edit, then you can see this window here. So we use these parameters for this simulation, and then if we use kinetic settings, which is uniform distribution, for if you choose kinetic type, there are many properties you can select, but here we select beta, which means beta is equal to angular frequency divided by, angular frequency divided by phase velocity. Yes. So we use these parameters for this simulation, and then after this case, we can define analytic magnetic source field. So this is for focusing the electron beam. Generally, this can be defined as between 0.5, 0.6 to 0.7 Tesla. Can be defined this. Why do we use this? It's used for focusing structure of electron beam.
This magnetic field is along the full length, or
Along the axial direction. Yes.
it's a huge field?
Yeah. So this is a peak position monitor. This is step width, so we can obtain some results by using this peak position monitor, and we can define peak particle in cell phase space monitor, and we can use this ordinate by selecting energy, velocity, and other type of things we can select from there. For example, we use here energy for y-axis, and this is x-axis for position or whatever you want. We have lots of choice here. So we can plot energy with respect to position here. But we can also plot velocity with respect to position. We can plot also. Okay. This is a particle monitor, current versus time and power versus time. If we choose them for collision information, I don't have any experience about collision, but maybe you can explain this collision.
Sort of collision, maybe you can.
Yes,
Electron.
you can explain collision. Maybe you
I think it's space charge. Yeah.
Space charge?
Space charge.
Okay.
But if you choose the
It's
periodic emission
it's
model,
far away for me now, but I can learn
if you choose
this
the
collision.
if you choose the thermionic emission model, then this thing is already incorporated. But you're choosing the DC model for emission.
Yeah.
Then you have to keep the collision thing maybe for the space charge.
Okay. Yes. So we have another particle monitor. This is for I think this is Helix. I guess this is Helix and this is boundary background. We can select this, and after this selection we have excitation signal. We can define excitation signal here. This is our tube, our traveling wave tube. We have here input and output, couple output part of this tube, and we can define excitation signal. We can define signal type here, sine step, and we can define frequency, T rise, and we can define analytic magnetic source field. This not right. This 0.8.
I
0.8.
don't understand where you define the RF input or RF output.
Yeah. Actually, I didn't put the slides, but I modify it. We select this part. We select this part to add port. This is port 1.
How much time does it take to analyze?
I will show. I will show the following slides.
Okay, and how many mesh analyzes maybe you also?
Yeah, of course. I can explain that 1,500,000 meshes, I think.
Do you ever use unit cell analyzers?
No, this is not unit cell analysis. This is just hot simulation. It's particle simulation.
And artificial intelligence do you use? Or
No.
In
We can use
Yeah.
some optimization technique. We can use some optimization techniques to improve something else. For example, efficiency. We can use, but in this simulation we don't use.
I see.
Okay, this is not right value. I update this one. The right value is 0.8 for this simulation. So this is also not right value. I update this part of slide, and the right number is 30 nanosecond. 30 nanosecond. The right number.
Excitation signal is Gaussian.
Yes, Gaussian. And this is right simulation time. This is right simulation time, and we have here input port is port 1, and amplitude square root of 0.1. This is our amplitude, and this is our signal, and this is our reference frequency. So this is our simulation parameters here for this peak simulation. If we simulate this, then we have actually this is our simulation time for 30 nanoseconds. For 30 nanoseconds, the simulation time is 5 hours, 32 minutes, 42 seconds for in this laptop. This is ordinary laptop, and we have these properties of this laptop here. This is our property of this laptop. So this simulation time we have, and this is our simulation result of analytical magnetic field here. This axial direction. So this is 0.7. You can see. Theoretically, this magnetic field, predefined magnetic field, can be determined, can be adjusted, or can be determined by this equation. We can use this equation, and this is beam current, and this is I think this is beam reduce, as far as I remember. And we know this vacuum parameters, and I don't know this, but I can. Do you know?
Maybe this B is the radius of the magnet. So
Radius of beam?
Magnet.
A magnet. Okay,
Magnet.
sorry.
And IB.
Yeah,
is
you
the,
are right. Magnet.
IB is the
Beam current.
the current flowing in the magnet, because that eventually this is going to be an electromagnet.
Okay, sorry. Yes. So this is eta. Maybe interesting
Maybe there's some
something.
scaling thing. I have to check. Maybe some number of turns, something like that, because of different turns.
I should check the equation. But this is how to determine predefined magnetic field here. And this is a particle view of a particle preview of our simulation. We have here velocity modulation of the particles by different colors here. This is electron volt here, electron volt, and this you can see we have here bunching. This. We have here bunching. I think this is just figure. So, other slides. Yes, we have, I think, video here.
The electromagnetic mode important here, TET and TE1.
No, this is just energy. It's just energy. So we use we can see particles movement here.
But somewhere some mode is excited inside.
What?
Which
Yeah,
mode is
of course.
TEM mode. Very
Yeah, we can say TEM mode due to we have two conductors, so we can say this. We have TEM mode. EM mode. And I have video. Okay, so.
What is the version of your CSD?
Yes, this is 2024.
Electron, not-
Yes.
The 2021, there's no any specific pattern for the yes, just I.
Yes.
What
Yes, on AI, that's what it is.
is the main structure
Same.
is important.
I agree.
It's loading, I guess.
Yes, I think so.
Wow.
I think so. Yeah, we have time, but have to wait.
This, you see that white bar? at the
Yeah.
bottom?
It's continue.
Okay, it doesn't matter. I can show. This one. Yes, this one. Yes. This is 30 nanosecond simulation of particle preview. You can see here we have bunching points with red colors here. This is 30 nanoseconds simulation. Here we have energy. We have energy, and this is velocity modulation, you can say. And next slide. Yes, we have here input and output signal of these traveling wave tubes here. And we have this is the input signal of port 1. And if we choose amplitude of this signal, this red curve, we have, sorry, this is the right one. I update this. So this the right one is this value. So has an amplitude of this with unit square root of watt, and the output signal, if we sketch a horizontal line, and then we can read this number here. So this is the wrong one, and this is 30 nanoseconds actually, not 10 nanoseconds. So for this simulation, for this traveling wave tube, we can say gain. We can calculate gain by using the amplitude of this simulation, this signal, and we have 4.34 dB here.
Is the vertical line is power or voltage?
Vertical line is power with square root of power.
Square root of power.
Yeah.
Okay.
Yeah.
Because
Square root of power.
if square root, that's correct, I guess.
Mhm.
Because 20 times the logarithm is about voltage.
Yeah.
Now.
Uh-huh.
I can't see it square root.
Square root of power.
Yes.
Sorry. I update these values. This is the right one. So this is 30 nanosecond. This is the right values. Okay. And this is the velocity of particles after nearly 29 nanoseconds. This is the velocity of electron beam with respect to position, actual direction. So we can see it starts from 0 here. It starts from 0 and becomes growing like this, but this is oscillating, you know. We have after 120 or 120 millimeter, we have here these numbers of these numbers with this electron beam velocity. So we have this frame. This is frame number 119. So we can see here many particles, you know, this 956 point, not 900, 9056.770 particles here. Yes, and this is beta. So we can obtain velocity from beta. And this is the energy of particles from 0 nanoseconds to 30 nanoseconds. I can show frame by frame here. So this is 0.25 nanoseconds particle. Here we have energy for this position, and then it becomes growing. Here, this 5.5 nanoseconds and 13 nanosecond and 18 nanosecond and 24 nanoseconds. So you can see growing of energy here. And finally, we have this energy here. We use peak phase space monitor. So the purpose of this lecture is to describe particle simulation of a simple, not a simple, but this is a CSC example of trunk wave tube. So in present of test analysis, which means gives information about game results of beam wave interaction. So I say many thanks to Dr. Hastekeoğlu and Dr. Nesil and all of lecturers to attend this great event. It was a great experience to share your thoughts and study it here with you. I'm looking forward to attend another important event like this. Thank you.